workshop, give a more general talk or talk for a more general audience about some subject related to the subject of the workshop. So today we're pleased to have Richard Wentworth talk about Higgs bundles, connections, and higher psychometrics.
Thank you very much, John. It's a pleasure to be here, and I'd like to thank Laura and Sasha for inviting me to. I think I'd like to thank them for inviting me to this colloquium. It is going to be a colloquium, and so if I do my job correctly, that means that for the first 30 or 40 minutes or so, hopefully I'll say something new and interesting to the people who are not participating in the workshop, and I'll say nothing new and interesting to the people who are participating to the workshop. So that's kind of my goal. So the topic is a big one, Higgs bundles. Of course, this is a very active area, and I think it's probably pretty impossible to give any kind of a survey of the field in 1 hour, and in any case, I'm probably not the person to do that. Anyway, so instead of doing that, I thought I would concentrate on some aspect that kind of links the higher rank theory, the Higgs bundle theory, to something more classical in Teichmueller theory. And so this is hopefully an illustration of this non-abelian Hodge correspondence that everybody's talking about. Okay, so as an outline, I'll start by just kind of reviewing the construction of the moduli space, and the point of view I'm going to take is that of hyperkähler reduction. And then I'll say something about the Higgs moduli space. I probably will avoid, in some sense, the most interesting aspects. I'm going to again concentrate on the ones that are important for what I'll say later. But at least I'll define a couple subspaces of the Higgs moduli space that have very clear classical analogs to sort of illustrate that this is an interesting moduli space to be looking at. And then the main topic is really some computation of variational formulas. And if I have time, then I'll say something about a metric on the Hitching component called the pressure metric, which is a generalization of the Weil-Petersson metric. Okay, so let me begin from the point of view of hyperkähler reduction. So let's start with symplectic reduction. So this is something that probably everybody's very familiar with, but let me just review it quickly. So let's start with a symplectic manifold, and compact or non-compact. This is technical issues that I'm just not going to really worry about too much in a colloquium, but let's say if you like a compact symplectic manifold, and a compact group a Lie group acting on that symplectic manifold via symplectomorphism. So it pulls back the symplectic form to the symplectic form. So a moment map for this action is a map to from the symplectic manifold to the dual of the Lie algebra, and it's defined via this differential definition here. So here C is an element of the Lie algebra, and C sharp is the associated vector field on the symplectic manifold that Lie algebra element induces. And so the moment map is defined in this differential way. So there is an existence question here about whether you have a moment map or not. And again, I'm going to sort of ignore that and assume that we have a moment map. So in the case where we do have a moment map, then the symplectic quotient, the Marsden-Weinstein symplectic quotient, is gotten by taking the zeros of the moment map and dividing by the group. And the key point is that this now, at least at the smooth points, is now inherits a symplectic structure from the original symplectic manifold. So it's a way of constructing new symplectic manifolds out of old ones that have some sort of symmetries.
Distribution actually replacing zero by something non-zero?
So that's right. So in the case where the Lie algebra where the Lie group has a center, for example, then this moment map may not be unique. So this is a G equivariant moment map. So if I do have a center, I can add something in the center that'll still be a G equivariant moment map. So I'm not claiming any uniqueness. And so in that case, in particular, I could take any point that's that's equivariant, right? Because so G should preserve this point, right? So I can take any point that's, say, like in the center, and I can still do the reduction there. And asking the question about how the reduction varies as I move around the center is an interesting question. Okay, so that's definitely something one can do. All right, so now let's suppose that we introduce some holomorphic geometry here. So suppose that, in fact, I have a Kähler manifold, and the complexification of my Lie group acts holomorphically on the Kähler manifold. And I'm going to suppose furthermore that the symplectic form is integral. And so there's a holomorphic line bundle with a Hermitian structure. And the curvature of the Hermitian structure is a multiple of the symplectic form. Okay? So then, in this case, then the existence of a moment map is essentially equivalent to a lift of the group action to the line bundle. This is sometimes called a linearization in the geometric invariant theory language. And so then we can make a definition, sort of an algebro-geometric definition. So a point in the symplectic manifold is called semi-stable if I can detect it via some section of some power of the line bundle. Okay, so there's some section of a power of this line bundle that is non-vanishing at that point. And then the geometric invariant theory construction is to look at the semi-stable points and take a quotient. So there's a further identification one has to make that is not going to be terribly important. But in any case, in this situation, by throwing out unstable points, the bad points, then I get a good quotient. And so, for example, like in this case that I'm describing here, the Kähler manifold is actually projective algebraic. In that case, the quotient will also be projective algebraic variety. Okay? So now the thing that links these two pictures is the Kempness theorem. So the Kempness theorem, let me try to state it in the most compact way possible. So it turns out that we can, as I said, the existence of a moment map is essentially equivalent to this linearization of the action. So now I have two quotients, the symplectic quotient and the GIT quotient. And the Kempness theorem tells us that they're the same, essentially. So if a point is semi-stable if and only if the closure of its orbit intersects the zeros of the moment map. Okay, that's the context of the Kempness theorem. And one can make finer statements that you'll see as we move along here. But the upshot is that there's a homeomorphism between the GIT quotient, something defined in the land of algebraic geometry, and the Marsden-Weinstein symplectic reduction. So this is the lingo is that symplectic reduction equals GIT quotient. So this is I don't actually know the history of this. I believe that it was certainly floating around. Probably Mumford had this idea originally, but in any case, Gilman, Sternberg, Kempness, and Atiyah-Bott. Okay, so that's the finite dimensional picture. And then in infinite dimensions, if one tries to carry out the analogous kind of construction in infinite dimensions, then things get even more interesting, because then the zero moment map condition typically corresponds to some solution to a nonlinear PDE. And the relationship with stability in algebraic geometry then is a question about whether a PDE can be solved or not. So let me give the most simple example of this, and maybe in some sense a good starting point for all others, and that is the picture of Atiyah-Bott. So let's start with a two-dimensional surface. So sigma is going to be a two-dimensional surface here. And in fact, in most cases, I'm going to think of this as having a Riemann surface structure. So if I have a Hermitian vector bundle, then A now, my symplectic manifold, is going to be the space of unitary connections. So this is an affine space modeled on the skew Hermitian endomorphisms, the one forms with values in the skew Hermitian endomorphisms of E. And it has a symplectic structure, and this is sometimes called the Atiyah-Bott-Goldman symplectic form, which I learned recently was well known to Narasimhan and Raman and Seshadri well before that. So in any case, the terminology sticks, I guess. But anyway, so this is this gives A a symplectic structure. And here, so nothing is compact anymore in this picture. Everything is by analogy. G is going to be the group of unitary gauge transformations acting on A. I'm going to identify the dual of the Lie algebra with the two forms with values in the skew Hermitian endomorphism bundles. So I'm going to use the killing form to identify the Lie algebra itself with its dual. And so then one can do a calculation and use the definition of the moment map and compute where the moment map is. And one gets that the moment map is the curvature. And as Nikita pointed out, there's always a central term that one could add here, and that will still satisfy the moment map condition. Okay? So notice that in this case, the square of the moment map is the Yang-Mills functional. Okay, so again, if I have a Riemann surface structure, then I can identify the space of unitary connections with the space of holomorphic structures on the bundles. So on a Riemann surface, there's no integrability condition. I can just take the 0, 1 part of my connection, and that defines a holomorphic structure on the vector bundle. And that's and conversely, in the presence of a metric, if I have a holomorphic structure, a d-bar operator, then I always get a unitary connection, the Chern connection. So this is an identification of this symplectic manifold with the space of holomorphic structures. I have a complexification of my group that acts here. So it acts on holomorphic structures, and therefore it acts on the space of unitary connections in this way, just by pulling back the d-bar operator. And so this leads to the notion of semi-stability of holomorphic vector bundles. Okay? And so there's no reason to write down what that definition is. You've probably seen it before. I'm not really going to use it again. But it's a very simple condition on a vector bundle that one can write down. And then the theorem that we've seen already many times in this workshop is the Narasimhan-Seshadri theorem. So a bundle is polystable if and only if it's isomorphic to one whose Chern connection satisfies this condition. And so this has a higher dimensional version, of course, and that's known as the Donaldson and Beckyal theorem. And so let me just say one or two things. So yeah, so here, of course, if I have this equation satisfied, then this constant C is topological up to some normalization of the area form. And in particular, if E is trivial, then this is a flat connection. C has to be 0. I didn't say what the line bundle and the linearization was. In this case, the line bundle is the determinant of cohomology, and the metric is the Quillen metric. And there's a lift of the action here, and so the GIT symplectic reduction kind of picture holds in more detail than I'm writing down here. But this is the upshot. Okay, so then the quotient, the symplectic quotient, or the GIT quotient, is then the moduli space of semi-stable bundles. All right, so now let's go to the hyperkähler picture. So I'm going to look at the cotangent bundle of this affine space. So it's an affine space, so the cotangent bundle is just trivial. And so here I will identify the cotangent space with the one forms of values in the Hermitian endomorphisms. Okay, and then again, if sigma has a Riemann surface structure, I'm going to stop saying that now and always assume that sigma has a Riemann surface. Then I get a hyperkähler structure. So I get several complex structures. One sort of coming trivially from intersecting, from switching rather Hermitian and anti-Hermitian, Hermitian and skew Hermitian endomorphisms, just flipping those two by multiplying by I, say. That would be, I think, J is typically what that one is called. And then the Riemann surface structure, the Hodge star operator, gives me a complex structure on each of these factors separately, and that's I, and then K is the product. And the group of gauge transformations acts symplectically for all the symplectic forms defined by these guys. And so now I'm in a situation where I have 3 moment maps. And if one, again, works out what these moment maps are, then one gets a modification of the previous slide. Here, from now on, I'm going to assume that my bundle is trivial. and not worry about Chern classes. So one of the moment maps is this guy, and then I get two others. So each one of these corresponds to the moment map for one of these symplectic structures here. Okay, and one can also think of these as the Euler-Lagrange, or the minimum of Euler-Lagrange equations for something called the Yang-Mills-Higgs functional. And in any case, I can take the quotient now by these three moment maps, and that's now going to be a hyperkähler manifold, at least at the smooth points. So that's a construction that I believe was originally due to Hitchin, Karlhede, Lindström, and Rocek. So this is the HKLR hyperkähler quotient. And that quotient is the Hitchin moduli space. Okay, so the Hitchin moduli space is the hyperkähler quotient of the cotangent bundle of the unitary connections. And so in particular, sitting inside of here is the cotangent bundle of stable bundles, but then it turns out there are more points. Okay, so let me look at the so where are the Higgs bundles? So let's look at these three equations, and let's focus on the last two. So these last two equations are harmonicity condition. So remember, psi is a Hermitian endomorphism valued one form, and so this is saying that one form is harmonic essentially, and so that's equivalent to saying that the 1-0 part, say, is holomorphic. And so that leads to the definition of what a Higgs bundle is. So a Higgs bundle is a pair of a holomorphic bundle and a 1-0 valued holomorphic endomorphism of that bundle. So since we're on a Riemann surface, I'm going to rephrase that like most people do and just think of this as a twisted endomorphism, a twisted holomorphic endomorphism of the bundle E. Okay. So that's what we get when we just look at the last two equations of the hyperkähler reduction, and so that leaves the original equation. And so if I rewrite it now in terms of the Higgs field, the 1-0 part instead of the full psi, then I get Hitchin's equations. And so one has to start with a Higgs bundle, and to find a point in the hyperkähler quotient that's isomorphic to that, one has to act by a complex gauge transformation, find a solution in the orbit to this equation. And that's exactly what the Hitchin-Simpson theorem does. And so let me phrase it in a way that's probably quite different from the way they thought of it. But so a Higgs bundle is semi-stable if and only if the closure of its orbit, here the complex group acts by acting on the holomorphic bundle like it does, and then acting by the adjoint action on this Higgs field. And so the statement is that if it's semi-stable, then the closure of the orbit contains a solution to the Hitchin equations. And moreover, if it's stable, then in fact the orbit intersects the space of solutions. Okay, so this is what identifies semi-stable Higgs bundles, the moduli space of semi-stable Higgs bundles with this hyperkähler quotient. On the other hand, one can look at the first two equations. One can look at the first two equations, and so these are the first two equations of these three hyperkähler moment maps. And so these equations are equivalent to saying that this new connection is flat. Right? If one just works it out, then flatness of this guy, this is the skew Hermitian part of the curvature of Nabla, and this is the Hermitian part. So those two separate out, and so flatness is equivalent to these two equations. So this is not a unitary connection anymore, because psi is a Hermitian part. So it's a unitary plus Hermitian endomorphism, and so this is in general just a connection with values in GLNC or SLNC. Okay. All right, so one could start with flat connections now and ask whether you can solve the third equation. So this is the third equation that I'm repeating here, and so now the gauge group, the complex gauge group acts as well on flat connections. And let me just warn you that this action is different from the one that I defined just a minute ago on Higgs bundles. Right? So this action just takes the connection and pulls it back. And that's an action on SLNC connections, flat connection. It preserves the flatness condition. So this action is actually different from the other one, but nevertheless we can use it and ask whether we can find in its orbit a solution to this last equation. And that's the other side of this story. In this context, it was proved by Corlett and Donaldson, that says that if you have a so it turns out that the closure, in this case, the closure of the orbit always contains a solution, and if the flat connection is semi-simple, then in fact the orbit intersects. In fact, that's an if and only if statement. So the orbit is going to intersect the solution space if and only if the flat connection is semi-simple. Okay, so if I now define the de Rham moduli space as the space of gauge equivalence classes of flat connections, then what the two sides of the story has just demonstrated is that there's a well, we haven't really proven much about the structure of this correspondence, but in fact it's a homeomorphism or a diffeomorphism, if you like, on the smooth points, and this is what's known as the non-abelian Hodge correspondence. Okay, so any questions so far? As I say, I think workshop people are probably getting a little bit bored, hopefully. Okay. I'll say something interesting later on, hopefully. Okay, so you have this correspondence, and so now you want to study it. And so, again, there are many opinions probably about this, but from my point of view, here is the motivating problem. On the left-hand side, we have the moduli space of Higgs bundles. And when I think of Higgs bundles, I think of holomorphic data. And on the right-hand side, we have the moduli space of flat connections. So I think in terms of holonomy and representations. And there's some transcendental, very transcendental nonlinear correspondence between those two spaces. And the question is, how do you understand it better? How do you probe it? What is one phenomenon on one side say about corresponding phenomenon on the other side? So one problem that I would say is rather central to the subject is to relate in a more direct way the holomorphic data that sort of lives on the Higgs side in a natural way to geometric or even dynamical data. I'll say more about what I mean by that later on, but let's say geometric or dynamical data on the flat connection side. And by analogy with the rank 1 case, you might expect to see periods of holomorphic differentials coming in. And so that's kind of what I would like to illustrate with the next part of the talk. Okay, so let me say something about the Higgs moduli space, about not so much about its structure, but what I would like to do is define two natural subvarieties of the Hitchin space. So let me start out with in the rank 2 case, which is the easiest one, the original one that Hitchin considered after all. And let's consider a particular example of a Higgs bundle. So I'll take a square root of the canonical bundle, a fixed one, and look at this bundle that is just a direct sum. So this bundle is not a stable bundle, but if I add this Higgs field, so this is a Higgs field, and this actually makes sense because in the lower part of this endomorphism part, that's mapping the first factor to the second factor. So that's a section of the anti-canonical bundle, but the Higgs field is supposed to be in the canonical bundle tensored, the endomorphism bundle, and so that's the corresponding entry here is a section of the trivial bundle, so it makes sense to put a 1 there. So that's why this phi sort of makes sense as a Higgs field. Okay, and so when you do that, then it turns out that this guy is stable, and in fact we even know what the solution is in this case. One of the very few cases where we actually know what the solution to the Hitchin equations is. Namely, I can just take the constant curvature metric on the Riemann surface insofar as I know what it is, I know what the constant curvature metric is. So I can just take that metric and I can just make this an orthogonal splitting. That constant curvature metric induces a metric on the spin bundles, and I just use that metric, and voila, I have a solution to the Hitchin equations. Okay, so it's rather direct in that case. Okay, so now we can modify this slightly by adding in a quadratic differential. So take a quadratic differential, a holomorphic quadratic differential, and stick it in to the part of the Higgs field where it belongs, namely in this part. And again, one has a well-defined stable Higgs bundle. And now the solutions to the Hitchin equations are more complicated. But nevertheless, by the correspondence, we know that those solutions exist. And in fact, we know enough about what those solutions look like to know that the representations, the holonomy is real. And in fact, this sweeps out an entire component of the representations in SL2R of the fundamental group of the Riemann surface. And in fact, this is a particular component. It's the one with maximal Euler class, and it can be identified with a copy of Teichmueller space. And in some sense, this identification was already known by work going back to Eels and Sampson and Wood and Shane Yao and others. It was finally a theorem of Mike Wolf that proved that essentially what I'm writing down here is really diffeomorphic to Teichmueller space. And so I didn't really tell you how the Corlett-Donaldson theorem goes, but it goes via equivariant harmonic maps to associated symmetric space. In this case, for SL2R, the symmetric space is just the upper half plane. And so these are just equivariant harmonic maps from the upper half plane to itself. And so these, for discrete faithful representations, this just corresponds to harmonic maps between Riemann surfaces. And so it was a theorem of Mike Wolf that if one looks at the space of harmonic maps between a given fixed Riemann surface, like we're doing, we're fixing on our Riemann surface sigma. And if I take a hyperbolic metric on any other Riemann surface and look at the degree 1 map there, find the harmonic map, what I get from the harmonic map is a Hopf differential. So this Q then is the Hopf differential. This is one of the few cases also where we can really identify the differentials that appear in the Higgs bundles with really concrete geometric objects. This is the Hopf differential, namely the pullback, the 2-0 part of the pullback of the hyperbolic metric on the target. And what Wolf proved was that this sets up a diffeomorphism of Teichmueller space with the space of holomorphic quadratic differentials. So of course that's a rather strange diffeomorphism. You certainly don't see the complex structure of Teichmueller space coming from this identification. But it is rather significant in the following sense. Let me just say this because this is kind of an interesting point, is that if one makes this identification, then one also kind of naturally has a compactification of Teichmueller space just by adding the sphere at infinity in the space of quadratic differentials. And that sounds very implausible, but it turns out that that is actually a mapping class group invariant compactification. In fact, it's the Thurston compactification. So if one tries to do that with Teichmueller's parameterization of Teichmueller space, then that doesn't work. But the harmonic map picture is sensitive enough to, at least in the large, is sensitive enough to see the correct compactification of Teichmueller space. Okay, so again, you've got a copy of Teichmueller space sitting inside of the rank 2 moduli space of Higgs bundles. Okay, so there's a higher rank version of this, and so in fact Hitchin showed that if you look at SLNR representations, in fact he proved a more general theorem, but I'm going to stick with the SLN case. So if you look at SLNR representations, then he counted the number of components actually, And he proved that one of them is diffeomorphic to a space of differentials. And so now when we go to higher rank, we have to take differentials up to, we have to take as many powers of k as the rank of the group. So there are n minus 1 powers of k that appear. And so Hitchin showed that there's a natural diffeomorphism, which I will say more about later, between a full connected component of the SLNR representation variety and this space of differentials. And so this component now is something that we call the Hitching component. And in Hitchin's paper, he's sort of said that this seems like an analog of Teichmueller space, and in the sense that it's a contractible component. It's diffeomorphic to a space of differentials, but that was about it as far as his comments on that. But since then, we've understood that the representations that live here in this component are very special. So, for example, they're all discrete and faithful representations, and they have interesting dynamics. They're what are called Anosov representations. So there's a lot of work that has been done that sort of reinforces the idea that this deserves to be some sort of a higher rank version of Teichmueller space. And in particular, with respect to the Atiyah-Goldman symplectic form that I mentioned earlier, this is a symplectic submanifold. So just like Teichmueller space, it has a natural symplectic structure, mapping class group invariant symplectic structure. Okay, I'll come back to this later on. And so let me introduce another subspace of the Hitchin moduli space from the point of view of differential equations. So let's look at ordinary differential equations. So here, y and q are just holomorphic functions. So I have a second order differential equation on a disk, say. Okay? And then you'd like to ask the question, can you put this differential equation onto a Riemann surface? And then you realize that things should transform according to some sort of tensorial properties. And so after some fiddling around, you see that you should really think of y as being a local holomorphic section of an anti-spin bundle, if that's the right terminology, an inverse, the dual of a spin bundle, a section of k to the minus 1/2, and q should be a projective connection. So q is almost a holomorphic quadratic differential. If I didn't have this extra term here, this would be an ordinary holomorphic quadratic differential. It's not quite that. It transforms according to what's called the Schwarzenegger derivative. Okay, so there's this extra term here that prevents this from being an honest quadratic differential. But one way to think of this is that at least for Mobius transformations, if these were restrictions of Mobius transformations, this term vanishes. So this would be an honest holomorphic quadratic differential with respect to Mobius transformations. So I guess this is what a physicist would call a quasi-primary field. Just thought I'd throw that out there. Okay. All right. Yeah. So then once you have this a projective connection, then I can write down this differential equation. This is something that makes sense on the Riemann surface now, and I can take two independent solutions and analytically continue them around the surface, and then there's a monodromy that arises from that. And so if I look at this, so in particular, I get a representation into, well, normally you get a representation into PSL2C, but choosing this square root of the canonical bundle essentially is what lifts it to SL2C. In any case, the monodromy is going to, the collection of monodromies that I obtain in this way ends up cutting out a half-dimensional submanifold of the space of representations. This is essentially the de Rham moduli space, right? It's actually the Betty moduli space, but this is essentially the de Rham picture of the Hitchin space that I was talking about before. Okay, and so in the case of SL2, these are classical objects called complex projective structures, and their higher rank versions also exist, and so they have the name of opers. Okay. And so this submanifold is actually Lagrangian with respect to the Atiyah symplectic form. Okay. So there's a common point to both of these, coming from Fuchsian representations. So let me finally introduce this notion. So if I have a representation into SL2R, say a discrete faithful representation, so a Fuchsian structure, a Riemann surface structure that I've uniformized on the upper half plane, and furthermore lifted to SL2, which I can always do. So if I have this representation, then I can compose it with the irreducible embedding of SL2 into SLN, and look at the corresponding representation into SLN. So this gives me a copy of Teichmueller space, or the Fricke space, if you like, the representations into SL2, the discrete faithful ones, gives me a copy of that sitting inside of the SLN representation variety. And so we'll call that set the Fuchsian locus. Okay, so representation into SLN is Fuchsian if it arises in this way. Okay, that's my definition. It's not my definition, but it's somebody's definition. Okay, so another way to think of the Hitching component that I was just talking about is that this is the component of the SL and C representations that contains, SLNR. This should be SLNR representations that contains the Fuchsian locus. Sorry about that. That should be an R right there. Okay, so let me try to describe the Fuchsian locus both from the point of view of Higgs bundles now and OPERs. Okay, so it's a common point in both, and so probably the slickest way to do this is to think in terms of the principal embedding of SL2 and SLN. So AXY is my basis for SL2. A is the Cartan element, and X is the raising operator, Y is the lowering operator. And so SL2 then acts on SLN. And so I can decompose SLN in terms of the irreducible SL2 representations. And the EIs and FIs are going to be a choice of highest and lowest weight vectors for each of those representations. Okay, so it turns out there are n minus one of them. So the E1 and F1 correspond to X and Y, and then I have the other guys. Okay, so there's some choice involved there, but that I'm not going to get into. But there's kind of a natural way to normalize that choice of highest and lowest weight vectors, at least up to sign. Okay, so then furthermore, let me decompose then the endomorphisms of E. So E now is going to be this rank n bundle, which is the symmetric power of that bundle that I started with before, and then that endomorphism bundle has a natural action of SL2, and I'm going to divide up into the A weight space in this way. So this should be the traceless endomorphisms. Whenever you see that from now on, that's going to be traceless endomorphisms. Okay, and I'm going to think of this as a Hermitian vector bundle, actually, with the metric as before, the metric coming from the constant curvature metric on sigma. Okay, so then it turns out that, so I guess I didn't say this, but so Y lives in the space, so Y lives in the space where m is minus 1. So, I guess I kind of said that in words, but if one checks, right, I did say that in words, right? The A weight of Y is minus 1, and so it lives in this minus 1 space. Then I'm tensoring by k to the minus 1. To get a Higgs field, I have to further tensor by k. So again, just like before, it makes sense to take an element of the G minus 1 space, and that is a Higgs field, right? That's a trivial bundle sitting inside of this endomorphism bundle. And so it makes sense to talk about Y as a Higgs field, and in fact that is the Fuchsian, that is the Higgs bundle corresponding to the Fuchsian representation in this SLNC. Okay, so the Higgs bundle, this is what Zhongling wrote down, I guess yesterday or the day before, and this is just a way of thinking of that in terms of the principal SL2. Okay, and then now how do we think of the Hitching component? So we're going to add differentials, and this is the way we do it. So if I take differentials, these are the degrees of the differentials from 2 to n, then if you go back here and think about these weights, then this is an element of the of K tensor the endomorphism bundle. Okay, so the I plus 1 weight here, let me just remind you back here, this is K to the M, so this has one more degree than it should, but that's good because the Higgs bundle further tensors by K, further twists by K. Right? So this is living in the right space. So this phi of Q is something that we can add to get the Higgs field. And so now we can think about the Hitching component. The underlying Higgs bundle is always the same. It's just this symmetric product of the trivial bundle. And the Higgs field is the original Y plus one of these phis. So this is the parameterization of the Hitching component. Okay, so that's how we describe the Hitching component. And now, similarly, we can do the same thing for a differential equation. So if I have a Fuchsian representation, then in particular, that gives me an atlas on the Riemann surface where the transition functions are Möbius transformations. So in particular, I have a complex projective structure, and I have a projective connection. So if you really want to write down what that projective connection is, then you can think of this uniformization as being an equivariant map from the universal cover of the Riemann surface to the upper half plane. You take the Schwarzenegger derivative of that, and that is a well-defined projective connection on the Riemann surface. And so, in other words, if I take that projective connection and I look at the monodromy of this equation, then I recover, up to conjugation, I recover the uniformizing group gamma. Okay? And so now we can just cook up differential equations of higher order that are satisfied by symmetric polynomials in the two solutions of this equation. So for n equal 3, for example, you would get a differential equation that looked like this, and then you can do some more. And so notice one interesting thing about this is that these things that appear here are not, of course, not differentials. They're not tensors even. They involve derivatives, and that is always the way it goes. So the leading order term will always be a multiple of a projective connection. And then the remaining terms are more complicated derivatives of the differentials that appear in the previous ones. Anyway, so this is the sixth order equation that corresponds to the Fuchsian rank 6 vector bundle. Okay, so now I would like to say something about deformation theory. So what does the tangent space look like at the Fuchsian locus? So this is a general thing. So again, we have these two pictures, right? We have the Higgs bundle side, or the Dolbeau side, sometimes people call it, and the de Rham side. So the tangent space to the space of Higgs bundles, so Tony talked about this earlier. This is a very simple version of that. So here, what is the tangent space to a Higgs bundle? I can vary the holomorphic structure in the bundle. That's a 0-1 form with values in the endomorphisms. That's varying the d-bar operator. Or I could vary the Higgs field. And the condition of being a Higgs bundle, when you differentiate that condition, you get exactly these equations. Okay, so these equations are very nice, very mild coupling between the two. But nevertheless, if you're at an arbitrary Higgs bundle, it's hard to realize explicitly what the solution space looks like in terms of holomorphic differentials. But at the Fuchsian locus, it's rather easy. In fact, it's a snap in terms of this SL2 picture. So indeed, at the Fuchsian locus, I can simply define these two guys like I did before, this phi, and for the other one, for the 0-1 part, I'll just take harmonic 0-1 forms and use the lowering operators. And this actually gives us an isomorphism. So these guys, in other words, satisfy these equations. They satisfy these equations sort of trivially. Well, not trivially. But the point is that for these guys, these equations decouple, right? Because in this case, phi is the lowering operator, for example, And so beta just consists of lowest weight vectors. So when I act by the lowering operator, for example, this is 0. So in fact, in this picture, these equations really do decouple. And I've got enough of them to sweep out the entire space. So that gives an explicit description. That gives an explicit description of the tangent space at the Fuchsian point, right? As the space of differentials plus its dual.
By same as the curly phi?
Yeah, this should be a curly phi. Yeah, exactly. Sorry about that. Okay, so again, the tangent space at the Fuchsian locus is naturally identified with the space of differentials plus its dual. Same thing in the de Rham picture. So the de Rham picture are flat connections. So I have to take, so the infinitesimal picture takes H1 with values in this local system, if you like, the closed one forms with respect to the flat structure, modulo the image. And here again, at the Fuchsian point, there's a natural identification with differentials and their duals, and this is the identification. So now we see some stars appearing. Okay, so again, one checks that this satisfies this condition of being closed with respect to the connection, but that's exactly this decoupling thing that occurred before. Okay, so everything works out nicely. So there are these two descriptions of the de Rham tangent space in terms of differentials plus its dual, and the Dolbeau one in terms of differentials and its dual, and you'd like to say that those are the same description, right? But what is going in between, the map going in between, is the non-abelian Hodge correspondence. It's the thing that relates the flat connection to the Higgs bundle. And so it's not completely obvious that these two descriptions of the tangent space are the same. What you need to know is that, in fact, the harmonic metric to first order is constant. And so this is true. It's kind of a nice theorem. I kind of like it. But at this particular point, the first variation of the harmonic map, for those Dolbeau variations that I was talking about, the first variation of the harmonic metric vanishes. So to first order, the Hodge correspondence it's trivial at the Fuchsian point. So as I say, in particular, that means that these two descriptions are the same. And I kind of think of this as an analog of an old result of Alfors. Actually, his first proof that the Weil-Petersen metric was Kähler went by showing that the area form, the first variation of the area form for a variation by a harmonic Beltrami differential was 0. And so this somehow is the higher rank version of that theorem. Okay. So that's a description of the tangent space. And let me just say, in terms of the parameterizations then, so at this Fuchsian point, we have two subspaces, one symplectic, one Lagrangian passing through there. The Hitching component is the symplectic guy. And this is how we identify. So this is a real identification of the tangent space of the Hitching component with a space of differentials. And it's this one. And I'm going to call that map psi. Okay, so we'll see psi later on. So I put it in there. And then for the Oper moduli space, this is a complex linear identification of the tangent space with a space of differentials. So a similar analysis appears from a different point of view in Peter Dalekov's thesis. Okay, so now I would like to use this description to compute some variational formulas. Okay, so what are the variational formulas that I want to compute? So here's a very classical one called Gardner's formula. So if I have so this is a theorem from Teichmueller theory. So if I have a simple closed curve on my surface, then I identify Teichmueller space as the moduli space of constant curvature minus 1 metrics. Okay. So for each point in Teichmueller space, I can look at the length of the corresponding geodesic. There's exactly one geodesic in that homotopy class, that free homotopy class, and I can take its length. So the length now is a function on Teichmueller space. Okay, and the question is, what's the derivative of this function? How do we compute the variation of this function? And that's what Gardner's formula does. So here it is. So if I take the derivative of this function in the direction of a particular Beltrami differential, So nu is a Beltrami differential, so its class is representing a tangent vector in Teichmueller space, then the variation of this length function associated gamma in that direction is the real part of an L2 pairing of the Beltrami differential with a certain quadratic differential. And what quadratic differential is this? This is what's called a relative Poincare series. So associated to a curve, a geodesic rather, I always have holomorphic differentials. These are called relative Poincare series. And here's how they're defined. So my gamma is a geodesic. So I think I take a lift of this geodesic up to the upper half plane. And in the upper half plane, it's a hyperbolic element. And so it has a repelling and an attracting fixed point on the boundary. And so I'll construct this one form, this holomorphic one form. And I'll take its kth power. Now, that differential is automorphic with respect to gamma, but it's not automorphic with respect to the rest of the Fuchsian group. So it doesn't define a differential downstairs, and so I'll just average over the rest of the group by pulling back this form. And amazingly, this actually converges. And it converges and gives a well-defined k differential on the quotient Riemann surface. And so that's what this is associated to. Okay? And so it's that differential, that quadratic differential that appears in Gardner's formula here. So we can think of this either as the pairing of the Beltrami differential with the quadratic differential, or if you prefer to think in terms of quadratic differentials, this is the hyperbolic metric. I can always go from tangent vectors to cotangent vectors, and then it's just the L2 pairing, or the Peterson pairing, if you like, between quadratic differentials. Okay, so now we come to periods. So there's another way to think about that pairing in terms of periods. Up to a constant, it's just the period of the k differential over the geodesic. So what do I mean by that? I mean, you compute this just like you do in calculus. So that's all I'll say. So that makes sense. And there's some nice combinatorial factor that appears. So the period of this k differential along the geodesic gives you exactly the Peterson pairing, the L2 pairing of the k differential with its relative Poincare series. Okay, so we have a higher rank version of this. So now we go to the higher Teichmueller space, or the Hitching component. No problem. So here, in general, I can do the same thing. So I have a representation in the Hitching component. I didn't say this, but this is a theorem of Labourie's, is that the matrices that appear in the representation are diagonalizable with distinct eigenvalues. And so it makes sense to talk about the highest eigenvalue of rho of gamma for any rho in the Hitching component. Or if you like, close to the Fuchsian locus, this is always going to be true anyway. So, but in any case, let's let lambda be the highest eigenvalue. So I didn't write this down, but in the case of the Fuchsian representations, this is e to some power that depends on n, e to some multiple that depends on n times the length. Okay, so lambda is like exponential of the length of the geodesic on the Fuchsian locus. So here I'm going to take a log, and when I compute d of the log in the direction of these variations, so this is only at the Fuchsian locus, then again, what we get is exactly the period of the k differential around gamma with some nice combinatorial factor here. Okay, so this is kind of a higher dimensional version of Gardner's formula. And we can do the same thing for the pth largest eigenvalue, and then you get even more impressive combinatorial constants coming out, but they only depend on ranks and p's and stuff like that. The key part is just that the variations are determined by periods of differentials. Okay, so that's one example of what I was talking about in the introduction, sort of trying to get some pairing of the non-abelian Hodge correspondence with periods of differentials. Okay, so let me give a result then on the symplectic structure. So again, going back to the case of Teichmueller theory, here's a result of Wolpert. So in fact, whenever you have representations of surface groups, then you can do what's called bending. So if I take a simple closed curve, that gives me a decomposition of the fundamental group in terms of a product or an extension of some sort. And what I can do is I can conjugate the representation on one side. So these are representations up to overall conjugation. So overall conjugation doesn't do anything as far as the moduli space is concerned. But I can take the representation and conjugate it on one side and leave it alone on the other side. And as long as the element that I'm conjugating by centralizes the monodromy around gamma, then this will glue together to give me a new representation. So this is called bending or twisting. And so when you do that with a hyperbolic surface, then it's even more geometric. You just take your hyperbolic surface, cut along a geodesic, and twist. Then that's what's called the Fenchel-Nielsen twist. And what Wolpert showed, among other things, is that twist is actually so that's a vector field in Teichmueller space. It's dual to this relative Poincare series for quadratic differentials. And moreover, it's exactly the Hamiltonian vector field for the length function. Okay, so this is kind of a key fact, and in particular, what you get out of that is Darboux coordinates for the Goldman symplectic form on Teichmueller space. Okay, so this is very nice, and another property that follows immediately from both of these points, the previous points, is a kind of reciprocity, which is useful if you take the twist around one geodesic and look at the variation of the length function of the other one. Then that's exactly opposite what you get by doing it in the opposite order. Okay, so this is reciprocity. So it turns out that something like this is also true for higher rank, for the Hitching component. Unfortunately, we can, as always, only do this at the Fuchsian locus. But in any case, we have a similar thing. So now, in this case, again, at the Fuchsian representation, or in general for Hitchin representations, the centralizer of an arbitrary element is going to be a copy of the Cartan. So we expect n-1 generators. And in fact, we have exactly n-1 differentials, as I said. And so we might guess that, in fact, those are spanned by the relative Poincare series, and that's true. So this is what we prove. At the Fuchsian locus, the space of twist deformations around gamma are spanned by the images, by this map that I have, right? The identification of differentials with the tangent space. When I apply that map to the relative Poincare series for differentials of degree k 2 to n. Similarly, the Hamiltonian vector fields of the eigenvalues. Oh, I should have said log of the eigenvalues. Sorry, this is log of the eigenvalues. That's the analog of the lengths. Log of the eigenvalues. The Hamiltonian vector fields are linear combinations of the twist vector fields around gamma. Unfortunately, that's not enough to prove Darboux coordinates, because now there are more vector fields that sort of interfere. And so we don't really have a Darboux description of the Goldman symplectic form in terms of these Poincare series. But maybe that's possible from this technology, at least along the Fuchsian locus. But we do get the reciprocity theorem here. Again, this is for an arbitrary eigenvalue and an arbitrary deformation degree of the Poincare series. Okay, so there's that's the symplectic structure, and I'm almost out of time. Let me just say just a couple things about a metric structure. So again, back in the case of Teichmueller theory, the Weil-Petersen metric is defined by, in terms of the co-metric, by taking the L2 pairing on quadratic differentials, or if you like, the L2 pairing on harmonic Beltrami differentials. That gives a well-defined mapping class group invariant metric. It's a Kähler metric. That's Alforz's theorem. And it turns out that it's an incomplete metric, which is interesting, causes problems, but it has the advantage of having negative sectional curvature. And so Thurston proposed a kind of dynamical definition of the Weil-Petersson metric, which very, very roughly speaking says that the Weil-Petersson metric at a point is the Hessian with respect to derivatives in Teichmueller space of the length of a random geodesic. Okay, so that probably is not saying very much, but one can be more precise about that definition. And in fact, one can be precise enough so that you can prove a theorem, and that's what Wolpert did. He showed that in fact this definition of Thurston is indeed a multiple of the Weil-Petersson metric. So again, the importance there is that Thurston's definition is entirely in terms of dynamics of the Fuchsian group and the variations of the Fuchsian group. And so somehow this definition that seems to involve a lot of the holomorphic geometry ends up being corresponding to a dynamical kind of picture. So
potential of the Weil-Petersson metric is the length function of random geodesics, so it's something else.
It's a different statement. No, it's not.
When you say Hessian, you mean literally the Hessian or the complex, the J invariant part of the Hessian?
No, it's the Hessian. It's the Hessian.
So it would still be the Kähler potential, but then you're making extra statement.
But this is a random geodesic. It's a random geodesic. So I take Hessians and then I take some sort of a probabilistic limit. So it's not the potential of a single geodesic. It's right.
If I make sense of this length function of a random geodesic as a function on the Teichmueller space, is it going to be the Kähler potential?
It would have to be the Kähler potential in particular, right? You could read off the part that was J invariant, but if it's actually the Hessian, that's saying that it actually satisfies something else. It's actually a homomorphic potential with Hessian.
So in physics, we know this as a Newell function.
That's right. So let me give you a slightly different definition. So let's take two surfaces. So what I can do there is take the length of a random geodesic over on this surface, where random is measured over on this surface. So that gives me a function, probably asymmetric function, but a function of two surfaces. You can show that that has a unique minimum, critical point, along the diagonal. You take the Hessian of that, and that's an alternative definition.
Sides of the derivative?
I don't know.
So it was
Well, in some sense, if by the random geodesics you mean actually the determinant of Laplacian.
No. See, to my knowledge, there's no relationship with that. But
when was this proposed?
oh, this is back in the 80s. So this is
After 84 or before it?
it's like, I don't know when Thurston did it, but Wolpert's proof is in 86. But it's a very, I don't know. I don't know the answer to this question. Okay. In any case, one can do this on the Hitching component as well. So there's a fair amount of technology that goes into that. So this is fairly recent. Oh, I'm sorry. I'm going over. So there's a mapping class group invariant Riemannian metric on the Hitching component that restricts to the Weil-Petersson metric on the Fuchsian locus, and its definition comes in this way. And so last theorem, so what we proved is on the Fuchsian locus, this pressure metric, so this is this metric that I just appeared in the last slide, on these particular variations is indeed a multiple of the L2 norm of the K differential, where this constant in particular depends on K. So there are sort of interesting consequences of this, but I've already gone over time, so I think I'll stop there.
Questions?
Can you find a combination of the largest and the next to largest and so on eigenvalues in such a way that this norm ceases to be k-dependent.
So this was a question raised by Jorn Andersen a few months ago. So this has both interesting and depressing consequences. So the depressing consequence is that one would like to show that the pressure metric is scalar with respect to the Goldman symplectic form. But this shows that this cannot be, because this coefficient depends on k. So that's kind of bad news. So we don't know the complex structure, in other words, but we see that it's not going to work for this. The metric and the symplectic form are just not going to be compatible with any complex structure. So on the other hand, this is kind of interesting because it does say that somehow the pressure metric detects the holomorphic differentials. It does give you the splitting in terms of differentials. So again, this is an example where the dynamics somehow sees the holomorphic geometry in a rather mysterious way. But as Jorn points out, there's not one pressure metric, there are a whole bunch of them. So this is the pressure, we did this for the pressure metric defined by the highest eigenvalue, but in the construction, in principle, one can use combinations of eigenvalues to define other metrics. And so it could be that for other combinations like this, that one can get something that is uniformly the L2 norm independent of K. But yeah, we just haven't been able to solve
But about high rank case, is there a kind of special situation when these things define the Darboux coordinates, like restrict to some subspace?
So
The generic monodromies, but
yeah, so I would like to do that, but as I say, so the results that we have on the twist deformations and things are not enough to give a full set of Darboux coordinates. But
It's the case when if you're in genus 0, genus 1, and all your punctures have a very special conjugate class with all other values equal but 1.
Right.
In this case, the information are not.
So it's so presumably in lower dimensional examples, it's
no, but what Nikita says, you can find restricted ones when you say that monodromies are not generic and maybe all of
So one other kind of set of
you have for any genus.
that's right. So one set of examples would be the ones that Zhongling was talking about. So there are certain subvarieties here in the Hitching component where the differential equation, the Hitchin equations, decomposes into a system of scalar equations. And in those cases, I think that all of these computations can probably be carried through, and one might have a chance of finding less coordinate stuff.
Any questions?